So, welcome back, and as promised, with today's lecture in section 4.4, we will complete knowing the derivatives of all the elementary functions when we take the derivatives of exponential and log functions. So, let's begin. And we begin by thinking about the number e. And e is a rather special number, and it's known as a transcendental number, and it shows up various ways throughout the course in calculus. We define E as follows. So E equals, by definition, the base of the exponential function whose slope at x equals 0 is 1. 1 is a rather special natural number. So that's how we define E, the base of the exponential function whose slope at x equals 0 is 1. This implies, then, that if we look at the definition of the derivative, we have the limit as h goes to 0. The derivative of e to the x at 0 is this: e to the 0 plus h minus e to the 0 all over h, and that has to equal 1. And what that implies, therefore, is that the limit as h goes to 0 of e to the h minus 1, because e to the 0 is 1, all over h must equal 1. So that is a direct implication of the fact that we have defined E as we have. And this is really important, and you'll see why as we continue. So we want to look at what the derivative with respect to x of e to the x is. By the definition of the derivative, we get the limit as h goes to 0 of e to the x plus h minus e to the x all over h. Now, we're going to use our properties of exponents and rewrite this as the limit as h goes to 0 of e to the x times e to the h minus e to the x all over h. Now, what's crucial here is that we have e to the x showing up here, and e to the x does not depend upon h. So h can go to 0, e to the x could care less. And so I can factor e to the x out, and in fact I can factor it out of the entire expression. And here's what I have. E to the x times the limit as h goes to 0 of e to the h minus 1 over h. So, does that look familiar? Does this look familiar? That's 1, as we showed before, based upon the definition of e. And so what we get is just e to the x. And so the big conclusion here is that derivative of e to the x is e to the x. And indeed, it's the only function whose derivative is itself. So now that we know that the derivative of e to the x is e to the x, we can answer the question, what is the derivative of e to the x? What is the derivative with respect to x of e to the u? And throughout all this work here, we'll assume that u is some function in x. And that will be consistent throughout all of our work coming up. So whenever you see u, think of it as a function in x. U could be x squared, u could be sine of x, u could be any function described in terms of x. And so this is equal to, using the chain rule, just e to the u times du dx. That's pretty simple. So now, how about if we look at a more general case? Suppose we want to take the derivative with respect to x of b to the x, and this is where b has to be greater than 0 not equal to 1. So again, we use properties of exponential functions, and we rewrite this as the derivative with respect to x of e raised to the ln of b to the x, which is the same as the derivative with respect to x of e to the x times the ln of b. So properties of logs, properties of exponents here. Please note that b is a constant, and so ln of b is a constant, and that'll be popping up throughout our work here. So what we have is the derivative of e to some function, and we've shown that that derivative is e to that function times the derivative of this. And that's just a constant times x, and so the derivative is ln of b. And this is usually written as ln of b times, well, remember this is just the same as b to the x. So it's the ln of b times b to the x. And that's what we get when we take the derivative of b to the x. Alright, so we just keep moving along. So we know now what the derivative with respect to x of b to the x is. So now we complete our study of the exponential functions, or the derivatives of the exponential functions, by asking the question, what's the derivative with respect to x of b to the u? And again, here we use the above result and the chain rule, and what we get is ln of b times b to the u times du dx. And that is all we need to know for taking the derivative of any exponential function at all. So now let's think a little bit about how we find the derivative with respect to x of ln of x. So we begin by saying, okay, let's let y equal ln of x, and really what we want is, what does dy dx equal? Okay, so we work in a similar way that we did when we were working with inverse trig functions. We take the statement that y is equal to ln of x, and we write it as its inverse relationship, which is x is equal to e to the y. And all we do now is differentiate, and we get 1 is equal to, using our rules here, e to the y times dy dx. So we were looking for dy dx, so dy dx is equal to 1 over e to the y. Before we start feeling too good, we really like to have these derivatives in terms of x. But all we need to do is look up here. Here's e to the y. It equals x. And so that tells me that this is equal to 1 over x. And that gives us the very, very important result that the derivative with respect to x of the ln of x is 1 over x. Pretty simple, and now we're on our way. So we just kind of lift it up one notch and we say, okay, how about the derivative of ln of u? Well, the chain rule tells us that that's just equal to 1 over u times du dx. That's pretty simple. So now we can ask the question, the more general question, the most general question for logs, which is, what is the derivative with respect to x of log base b of u? So we do the same thing as before. We say, let's let y equal log base b of u. What we can use now, by the change of base, is we can write y is equal to the ln of u over the ln of b. Now let's remember again, b is a constant, so the ln of b is a constant. We already know how to take the derivative of ln of u, And so therefore what we have is dy dx, let's just bring that constant out, times the derivative of ln of u, which is 1 over u, times du dx. And so this is the derivative with respect to x of log base b of u. And that's the big result that tells us how to take the derivative of any logarithmic function. So that completes the derivatives for exponential functions and log functions. And now we have a couple of interesting results from this. So as we have developed our study of derivatives, and we're looking at the derivative of just x to the n, if you remember, first we proved that this is equal to, let me write it like this, that the derivative of this was equal to n times x to the n minus 1. First when n was a positive integer, then when n was any integer, and finally when n was any rational number. And now let's extend it all the way to real exponents. So here's what we're looking for. We want the derivative with respect to x of x to the r, where r is any real number at all. And so we play the same game that we did before. We write this as the derivative with respect to x of e to the ln of x to the r. And we use our properties of exponents. And this is the derivative with respect to x of e to the r times ln of x. Now, r is a constant, so when we take the derivative of this, we'll keep that in mind. And the derivative of e to a power is just going to be e to the power times the derivative of the power, which is going to be r times 1 over x. So I'll rewrite this as r times, now remember again that this is just e to the r, so this becomes e to the r over, no, I'm sorry, let me change that. It's not e to the r, it's x to the r over x, and that's the same as r times x to the r minus 1. So the power rule works for real exponents also, and I suppose the easiest way to do that is just to go up here and say this rule is true when n is any real number at all. And that's a big result. And let's move along. So the last piece of the puzzle is known as logarithmic differentiation. And here's the simplest example. Suppose we're looking to take the derivative with respect to x of x to the x. Now, here's the issue. Because this is not a constant, this is not a polynomial. And because this is not a constant, this is not an exponential function. So x to the x doesn't fit into any of the categories that we've had so far. So we proceed as we have in the past. We say, let's let y equal x to the x. And if we take the natural log of both sides, we get the ln of y is equal to the ln of x to the x. Now this technique of logarithmic differentiation works because of the huge property of a log of something to a power, because I can rewrite this as x times the ln of x. So now if we look at the statement that we have, the ln of y is equal to x times ln of x, now we're just going to differentiate, and we get 1 over y dy dx equals, by the product rule, the first times the derivative of the second plus the derivative of the first times the second. And so what I'm looking for, dy dx, which is really the derivative with respect to x of x to the x, I multiply both sides by y but y is equal to x to the x. So I get x to the x times 1 plus ln of x. And that's a pretty simple example of how logarithmic differentiation works. So just again, we use logarithmic differentiation when we have something to a power, and both the base and the exponent are functions in x. And nothing could be simpler functions in x than x and x in this case. So there we go. And now we basically know how to take the derivative of just about anything that can come our way.